Supplemental math videos from Circle Christian School.
Trig fundamentals and identities.
In this chapter, we're going to expand our study of identities. We're going to find that the identities that we already know about will help us to identify other identities, and the identities generally will help us to manipulate trigonometric expressions and solve trigonometric equations. Well, here's what we know from the past. We know that we can use identities to identify the various trig ratios given this information. If we know that tangent theta is 2 and sine theta is less than 0, let's say that we want to find the other 5 trig ratios, and we want to use identities to do that. Now, we could use the right triangle idea and just use ratios, but let's use identities as much as we can. All right, now, if tangent theta is equal to 2, we have to figure out what quadrant we're in here. And the information from these two expressions will tell us. We know that tangent theta, if it's 2, that means positive, then tangent is positive in these two quadrants. So we're in one of these two quadrants. Now, sine theta, it says, is less than 0. So sine theta is negative. We know that sine is positive in this quadrant and this quadrant, but negative in this quadrant and this one. So if sine theta is less than 0 negative, then we must be positioned in this quadrant. Okay, with that information, then we know that our reference triangle occurs in this quadrant, and we can draw that reference triangle like this. We know that our angle, you see, appears in this quadrant. Our reference triangle appears here, and away we go with structuring the right triangle and identifying lengths of sides if we'd like to do that. All right, so tangent theta is 2. Now that's 2 over 1, opposite over adjacent, so we could set it up like this. Now, although it's 2 over 1 like this, remember that these are both negative values to make this 2 positive, and they're both negative because we're in the third quadrant. Now notice that I haven't really drawn this, the lengths of the sides anatomically correct. That really doesn't make any difference in this kind of context. Now, one approach that we could use here is to identify the length of this side by using the Pythagorean relationship. You know, the c squared equals a squared plus b squared. We could do that here, but let's use a different kind of approach. Because we're studying identities here, I'd like to go through the thought process of thinking about how we get into identities and use identities for this kind of purpose. All right, the first thing we can do is say, well, let's see. I have tangent theta is 2. Now, immediately I have another trig ratio because I know that there's a reciprocal ratio that's related to this one. It's cotangent. So we know automatically that cotangent theta is 1 over 2. All right. No, actually it would be negative 1 over negative 2, which reduces to 1 over 2. And I'm thinking about the reciprocal of that to give cotangent theta. Okay, that's another one. I'm going to put a box around them as I go because I want to have 5 boxes here. 5 boxes with that one gives us all of the 6 ratios. Okay, now I'd like to figure out some kind of ratio or identity that relates the given information or the information with what I know here with some other trig ratio. Now, the things that come to mind are the reciprocal relationships or the various Pythagorean relationships. Now, for the Pythagorean relationships, remember there are 2 trig functions related in each of the Pythagorean relationships. And the one that's easy to remember is sine squared plus cosine squared equals 1. That comes to mind perhaps rather quickly. The other 2 also involve 2 ratios, but they're not as easy to remember. But we can do this. Now, we may recall that, gee, I can't recall the others, and I think one of them involved tangent with some other trig ratio, but I'm not sure which one. Here's what you can do. You can just take the one that you recall, sine squared theta plus cosine squared theta equals 1, and then either divide throughout by sine squared theta or by cosine squared theta to generate the other 2. Now here's what I'm talking about. Suppose I elect to divide through by cosine squared theta. So I'm dividing this by cosine squared theta, divide here by cosine squared theta, divide here by cosine squared theta, and all of a sudden one of the other Pythagorean identities emerges. Sine squared theta over cosine squared theta is tangent squared theta, and this becomes 1, and 1 over cosine squared is secant squared. So here we have a relationship involving tangent with one of the other trig ratios, and we can use this information to solve for that one. We have information about this. All right, we know that tangent theta is equal to 2, so this is 2 squared then, plus 1 equals secant squared. So 5 equals secant squared theta. And by the way, we're using theta here as an angle, but remember that we could just as easily be talking about a real number and be talking about this radian idea as well. Okay, let's see. We have, if secant squared theta is 5, then secant is plus or minus the square root of 5. Now, plus or minus. Well, let's come back over here and examine things. Now, we know that in this triangular situation, in this third quadrant, secant is, well, let's see. Remember, it's the, let's see, I don't remember exactly what it is, but I know it's the reciprocal of cosine. And so I could think, well, what's cosine? Well, cosine is adjacent over hypotenuse. Secant is its reciprocal, so it's hypotenuse over adjacent. You see, so it's the idea that we're going to have this side over that one, and that's negative. You see, and this is always positive, so the fraction here, the ratio, is going to be negative. So secant then is negative square root of 5. So I can do this. Now, let's come back over here. Secant is negative root 5. That means that the hypotenuse here is the square root of 5, and this adjacent side is negative 1. So when we think of secant theta, it's the square root of 5 over negative 1, which is the square root of, excuse me, the negative square root of 5, which is what we found over here. Okay, so let me write that down. I'm going to just transpose it over here. So secant theta is negative root 5. Now, the reciprocal of secant is cosine, and I have that automatically then, so the cosine of theta is negative 1 over the square root of 5. And once again, I could go through the process of rationalizing. I think I'll do it in this particular case. It's square root of 5 over the square root of 5 that I'm multiplying by, so this is the square root of 5 over the square root of 25, which is 5. So now here we have cosine. Well, now that I have tangent, cotangent, secant, cosecant, I can now find sine and cosecant rather easily. All I need to do is come up with some kind of identity that involves one or two of these with sine or cosecant. And that's fairly easy to do. I can do this. I can think, well, let's see, tangent is sine theta over cosine theta. And you see, I know the value of cosine and tangent. I just figured those, I had this given and I just figured this one out. So I've got, let's see, tangent theta is 2. Now, I have a choice here. I can plug in to this relationship and then solve for sine theta, or I can solve this for sine theta outright and then plug in. I think I'll show you that method. It's pretty easy to see what would happen if we plugged in. But sometimes when fractions are involved, as they are in a lot of cases in these problems, it's better to go through and solve for a particular one of these first, like this. And then, you know, it's this kind of thing. Now we have tangent theta is 2. And cosine theta, we found it down here to be negative square root of 5 over 5. And that's what sine, whoops, that's what sine theta is. And now multiplying, we get negative 2 root 5 over 5 for sine theta. So then cosecant, and this is one of the others that we needed, and now cosecant is the reciprocal of this, so we have negative 5 over 2 root 5. And now we sort of have to rationalize back, don't we? If we multiply both numerator and denominator by root 5, we have negative 5 root 5 in the numerator. In the denominator, we have 2, the square root of 25. You see, I'm multiplying this by root 5 over root 5. Now this becomes 5, and this 5 cancels with that 5, so we have the square root of 5 over 2, and it, of course, is negative. So it's the negative square root of 5 over 2 for cosecant theta. And now I have all of the ratios using identities. Here's another one. Now, similar idea here, but I'm introducing a little nuance in each one of the examples to make sure we can handle a lot of different situations. This is sine of negative x. Now, notice that we're thinking in terms of real numbers here, but the idea is precisely the same as it was before. We're looking for identities to use in this analysis process. We have the sine of negative x is equal to negative 2/3, and the tangent of x is equal to this fraction. Well, it seems like we're given an awful lot of information here, but the first thing I want to start with is this notion of sine of negative x. And we talked about this in the past, but I want to make sure we have a good understanding of it. The study, or the idea, was that when we talk about negative angles, we think about what happens when angles are generated in this direction and angles are generated in this direction. The sine of negative x, you see, is an angle generated this way, and the sine of x would be an angle generated this way. And now think about where the sine function is positive or negative. Well, let's see. Sine corresponds to the idea of y, and the notion of y is positive in these two quadrants, but negative in these two. Okay, now, with that in mind then, if we're thinking about a negative angle of, let's say, 30 degrees. So we have negative 30 degrees, and up here we would have 30 degrees. Well, it's the idea that the numerical part of the answers will be the same, but the signs will be different, because the sign of an angle is negative in this quadrant and positive in this one. So it turns out that the sine of negative x is equal to the sine of negative x is equal to the negative of sine of x. That is, the sine of this negative 30-degree angle is a negative number, and it corresponds with the negative of the number corresponding with sine x, you see, or sine 30 degrees. Okay, so this is the idea. Now, of course, if this is true for sine, it's also true for cosecant. And this situation is also true for tangent and cotangent. That is, the notion of tangent negative x is equal to the negative of tangent x. And the reason for it is this, that if we're analyzing the notion for tangent and cotangent, you see tangent and cotangent are positive in this quadrant and this one, but negative in these two. And so as we come around like this, you see, our negative angles correspond with the negative of these positively generated angles. All right, so it's the same idea as we had with sine. Now, for cosine, it's quite a bit different. Cosine turns out to be positive in these two quadrants, negative in these two. So angles generated in either direction will have exactly the same value, wherever we are on the coordinate plane, wrapping around and so forth. So the cosine of negative x, let me write that down. The cosine of negative x is equal to the cosine of x. You see, they are precisely the same. Okay. Now, with that in mind, let's go through the process with this problem. All right, as soon as we have the sine of negative x, the sine of negative x is equal to the negative of sine of x, so the negative of sine x then is equal to negative 2/3. You see, those mean the same thing. So let's see, the minus signs can go out. So sine x then is 2/3. Good. Then we have, that's our first one, simplified. Cosecant then is the reciprocal Now let's turn our attention over here. Tangent x is negative 2 root 5 over 5. Well, gee, if we know that already, and that's one of the items that we needed to find, and it's already found for us, then we know that cotangent is the reciprocal, so it's negative 5 over 2 root 5. We had a similar situation in the previous problem. If I multiply here by root 5 over root 5 in order to rationalize, then I'll have, let's see, negative. Now, this is, well, let me show all the steps here. This is 2 to the square root of 25, which is 5, and this goes out with that. So we have negative root 5 over 2 for cotangent. Now we're ready to find, let's see, what's missing here. We have sine, cosecant, we have tangent, cotangent. We need cosine and secant. We'd like to find then some kind of ratio that addresses I have so many things to tell you at one time, I don't know where to go with this. We didn't talk about what quadrant we're in because we worked algebraically through this and just algebraically through this, and all we were doing was generating the reciprocals, and we could go through that kind of analysis right now. Let's wait on it though. Let's see if we really need that kind of idea. We're looking for an identity that involves, well, any of these, one or two of these, but also involving cosine. Now, it's pretty easy since we have tangent and sine. You see, we have tangent and sine to use that familiar one involving tangent. Tangent is sine over cosine. So we could come over to the side and write tangent x is sine x over cosine x. Now, from here, we might want to solve for what we're looking for. We're looking for cosine x. So we'd have to multiply on both sides by cosine x and then divide on both sides by tangent x to find cosine x equals sine x over tangent x. And we could certainly do that. But another approach that might be a little bit faster is to write a relationship like this in which the unknown quantity is in the numerator up here. And that way all we have to do is multiply on both sides by the denominator. Now that technique would be to just say, okay, well, cotangent is cosine over sine. Now I'm looking for cosine, so I multiply on both sides by sine. So I would have cotangent x times sine x equals cosine x, and I already know that cotangent x is this fraction, sine x is this fraction, and then it's a pretty easy idea to find negative root 5 over 3 for cosine x. And so anyway, it's just a technique. You don't have to use this technique, but it sometimes saves a little bit of time in certain situations. If you are aware of it, then I would latch on to it, because we do this kind of process so often that it might be worthwhile to try to think of situations where the unknown appears in the numerator of that fraction. Okay, if cosine x is this fraction, then that gives us the reciprocal relationship of secant x is negative 3 over root 5, and I'm pretty confident that we can rationalize that rascal at this point. Take a look at this situation. This is just another manipulation in a string of them. If we have cotangent over cosecant x, we sometimes can rewrite these fractions or any relationships that we see in various problems involving expressions or equations a little bit later. We can rewrite in such a way that we express our fractions in terms of sine and cosine, because sine and cosine are a little easier to deal with. I think they're a little more familiar to us than the bottom three ratios of cotangent, secant, and cosecant. So what we could do is rewrite cotangent x as cosine over sine, you see, and cosecant as 1 over sine, and then just manipulate this into a different form. Well, this is numerator divided by denominator. So it's this fraction divided by this one, and now it's times the reciprocal of this one, and these cancel, so we have simply cosine x over 1 or cosine x, a much simpler kind of expression to deal with than the original one. Before I start the next problem, let me mention again that we're just going through and showing a number of manipulations involving trigonometric expressions and using identities to simplify those expressions. And I'm just going through and showing a number of techniques here. And that's what we're trying to get out of this discussion. All right, we're going to simplify in this expression. But before we do, I'd like to remind you of a discussion that we've had before involving cofunctions and complements. That is, if we have this 30-60 degree right triangle, we know that the sine of 30 degrees, the sine of 30 opposite over hypotenuse is 1/2. The cosine of 60 is also 1/2. So the sine of 30 is equal to the cosine of 60, and we said that the cofunctions of complements are equal to one another. You see, that's a way of saying what's going on right here. And if we're talking about in the radian world, we're saying that the sine of pi over 6 is 1/2, the cosine of pi over 3 is 1/2. So same idea. Now, think about how we generate not how we generate cofunctions, how we generate complements. That if I were going to generate the complement of this 30-degree angle, then, and I know that we have some equality here, I would have the cosine of 90 minus 30, you see, to get at that 60-degree angle. And here when I'm generating a complement, I would take, let's see, if I want the complement of pi over 6 to be pi over 3, well, here's how I find it. It is, I take the, it's 90 degrees minus the given angle, or it's pi over 2 minus the given angle. So this is pi over 2 minus pi over 6, you see, to give the pi over 3 result here. Now, I just want to show the technique because when we see a situation like this, now notice this is cotangent of pi over 2 minus x. And when we see a binomial like this, it seems a little confusing at first until we realize that this is precisely the calculation that is needed in order to generate the complement of the angle x. That is, all this is the complement of x, you see, and so this can be rewritten in a very simple way. Now let me go through the algebra of writing the complement of that angle. The complement of an angle is found by taking the pi over 2 and subtracting the given angle. So it would be like pi over 2 minus the given angle. You see, if I want to show all of the proper steps, those go out and we have simply x. So this is nothing but the complement of x. Okay, now if it is the complement of x, then we can rewrite this as the tangent, oops, the tangent of the complement of this, but the complement of this we found to be x, you see. So this is nothing but tangent x times cosine x. And that's the technique, the main technique that I want to show in this problem. Okay, so that's the idea. Now we could take this problem a little further because we have an opportunity for cancellation if we rewrite tangent x as sine x over cosine x. So those go out and this becomes simply sine x. Here's a situation where factoring is the opportunity, and I see sine squared x here, I see sine squared x here. This is a single term and that's a separate term, so I can pull sine squared x out of those two terms as a common factor. All right, and that's the technique I want to show here. And by the way, you might see other manipulations in these problems, and we're going to see that an awful lot a little bit later, where we start to manipulate with identities. We're going to see a lot of times where we can approach the problem in 3 or 4 different ways and arrive at the same kind of result. But here, what I want to show is this, that we can take sine squared x out of these two terms. Now when I take sine squared x out of this term, I'm left with secant squared x. And when I take sine squared x out of this term, I'm left with 1. So we get this. Now how can we simplify from here? Well, of course, I could look at this and try to rewrite this in some other way, but no, I want to look over here. Secant squared x minus 1, that looks vaguely familiar. It might be related to one of the Pythagorean identities. It kind of looks like something I remember in the past. Well, in order to decide whether this is replaceable using a Pythagorean identity, what you might do, again, is just go to the sine squared x plus cosine squared x equals 1. And now just divide through by sine squared or cosine squared and see what emerges. Now if I divide, now I'm tipped off here that I want to have something in here that looks like secant squared. And I know secant squared is 1 over cosine squared. And if I divide through by cosine squared, I'll have, you see 1 over cosine squared here, secant squared. So that's my tip-off that I need to go through here and divide by cosine squared. So I'm doing this. Now a lot of times you'll find yourself doing this mentally. You don't really have to write it down. You can probably see through it in a lot of cases. But at any rate, we get this, and that of course goes out to give 1. And this is tangent squared x, and this is 1, and this is secant squared. Ah, well, this doesn't look like that. Oh, but wait a second, we can manipulate it into that form. If I subtract 1 on both sides, then I find this to be tangent squared x equals secant squared, oops, oh, I got it, minus 1. And so secant squared x minus 1 is equal to tangent squared x. So this secant squared x minus 1 is replaceable by tangent squared x. So that's what I'm going to do. And that's a simplified version. Now I could take this one step further. This is fairly simple in itself, but I could go a step further and I could think of tangent squared as sine squared over cosine squared. So I could write this. And then remember, this is over 1, so multiplying here I get sine 4th degree x over cosine squared x. Here's another one. Another factoring opportunity occurs here. It turns out that in this numerator we have the difference of 2 squares. And we can factor in much the same way that we factor the difference of 2 squares in earlier algebra. It's just an algebraic form that is similar to what we've had before. So secant squared x minus 1 is the difference of 2 squares. It factors into secant x plus 1 times secant x minus 1. And now I bring down the denominator. And oh, happy day, I see a cancellation opportunity here. So this becomes secant x minus 1. Here's a situation that just involves a simple substitution, or what appears to be a simple substitution. We have x squared plus 25 under a radical, and x is 5 tangent theta. Well, if x is 5 tangent theta, let's replace x with that value and just kind of follow our nose through the problem. This becomes, let's see, the square root of, now x is replaced with the 5 tangent theta, and it's squared. So the whole thing is squared, then plus 25. Well, let's go ahead and expand here. We have the square root of, let's see, squaring 5, we get 25. Then tangent squared theta plus 25. I see that 25 is in both of these terms, so I can snag out 25 as a common factor. And when I do that, I have, let's see, 25 times tangent squared theta plus 1. And wow, this looks a little familiar. Maybe this is one of the Pythagorean identities. I'm not sure which one it is. And if you're sure which one it is, just go ahead and pop the value in. If you're not sure, then you come out over to the side and you say, all right, I start with sine squared theta plus cosine squared theta, and I have something involving tangent theta, and that's easy to see that I need a sine squared over cosine squared, you see, in order to create the tangent squared. So I'll divide throughout by cosine squared theta, Now this becomes the tangent squared theta that I was after, and this becomes 1, and this is secant squared theta. But the tangent squared theta plus 1 is replaceable with the secant squared theta. So I come back here and we replace this with secant squared theta. And now, conceptually, let's stop right here. We're going to go one step further, but I want to make sure we understand what has happened here. We've taken a situation where under the radical we had two terms, and now using the identity idea, we have reduced this to a single term, you see, involving various factors. And now we can apply square root to each factor separately. And that's the great value in going through this process. So the square root of 25 gives 5. The square root of the secant squared theta is secant theta, and we're done.